Today we consider the first of two really important and quite different vector operations. The first is the dot product, the second is the cross product. Now, these are kind of like multiplication, but there are certain things you can do with vectors that you can't just do with regular numbers. So when you multiply vectors, that's why you have scalar multiplication, which is one sense of multiplying. Cross product is another type of product, and dot product is another. So let's go down and we'll just sort of differentiate these for you. And we'll start with our first one today, which is the dot product. So first of all, understand a couple of things. Let's draw this out. So we have three different types of multiplication using vectors. One you're already familiar with. It's called scalar multiplication. And basically the idea would be vector v, let's do it this way. So, kv, right, is the same thing as kv1, kv2, kv3. Okay, so basically scalar multiplication, what you're doing, you're taking each component of the vector, you're multiplying by whatever scalar that you were given. So if I say what is 3u, you would take the three components of vector u and you would multiply each one by k. Now, the one we're talking about today is the dot product. The one we're talking about tomorrow is the cross product. Now, just don't want to go too much into this right now, but when you dot two things together, it looks like this. Okay, so u, for example, dot v, okay, and you get a scalar as an answer. Okay, so u is a vector, v is a vector. When you dot them together, you get a scalar. Okay, just a really quick example. Let's say u is 1, 2, 3, and v is 4, 1, 3, and then we go dot. Right? If you type dot, what does it look for? It wants to know what two vectors do you want to dot together. So I'm going to dot u and v together, and it gives me this number 15. Just a regular number. It's not a vector anymore, right? Now, the cross product is a similar idea. Okay, it's u, except it uses this sign, and what it generates a vector. Okay, so when I say multiplying vectors, there are many different ways to multiply vectors, right? Like if you're using numbers and you stick two numbers beside each other, that means multiplication. If you dot two numbers, that means multiplication. If you put a times sign, that means multiplication. But in vectors, these are different things. So be careful. Scalar multiplication, dot product, and cross product are three different operations. They're all similar to multiplying, but they're not the same. Okay, the dot product gives you a scalar as an answer, whereas the cross product gives you a vector. Watch if I type cross, right? Cross, it wants a vector or another vector, so let's cross u and v, and it comes up with this other vector w. Okay, and we'll talk about how it does this and why it does this later, but just so you can see, these two things are very different, so don't mix up a dot versus a multiplication sign. So one of the most common things to use this for is to do for questions that involve work. I just quickly want to look ahead. Sorry, I should have done this before, but yeah, okay. All right, so for doing questions with work. Now, work is a quantity from physics that talks about how much energy, right, was done in order to act with some force over some distance. So it says Max is pulling his wagon up a hill with a force of 120 newtons at an angle of 20 degrees to the surface of the hill. The hill is 100 meters long. Find the work that he performs. The work performed is the product of the magnitude of the displacement traveled by the object and the magnitude of the force applied in the direction of the motion. Okay, so let's draw this, maybe make this a little bit easier to understand. So let's say here's the hill. Let's just make it very slight. And then let's say our object that he's pulling is like right there, and he's pulling it with with that many newtons. So what did it say? 120 newtons. But he's not pulling it all in the right direction, right? Some of it is being pulled perpendicular to motion. Only some of it is actually being pulled in the correct direction. So the idea would be we would want to find vector v, and then we would just want to take that force and multiply it by how far how far it was moved. Okay? So how would we do that? If you think about this triangle, right, we know that in this triangle, the little bottom corner is 20 degrees, because the question said that, right? And we also know that he's pulling with a force of 120 newtons, which is, all of his force, right, is sort of pulling in this sort of up and to the right direction. So how much of his force is actually useful for moving this object is 120 times cos 20. Okay, right? That would be the force that's actually down here. Okay, so the force in the direction of motion is 120 cos 20. What is that quickly? Let's just get that. Sorry, 120 times cos 20. Okay, 112.76. Now he's pulling this for 100 meters, so force times distance equals work. So 112.76 newtons times 100 equals 112.76 newtons. Newton meters or joules. So remember, for a unit here, you have two choices. Doesn't matter which one you choose. You either say Newton dot meters, right? So Newton dot meters. Just try and make that more obvious. Just do it like this. Okay, Newton meters or joules, right? So that's either one is fine for work. This is how much work it would be done pulling that object with that force over that distance. Okay. Now, so the work done was 11276 joules. Okay. This concept. So we took. So let's let's just go back to this quickly for 1 second. So let's say the hill is here, and vector A, and we're going to call this vector D. Okay, so this is the vector of him, pulling up the hill, right? Now the other vector was at an angle of 20 degrees, and it was 120. So we go 120. So let's go vector. Sorry, the hill was not 120. I'm sorry. This was. Let's rotate vector D 20 degrees. Sorry, this is his force vector, and his displacement vector. Right, this isn't going to work. Okay, so sorry. Let's call this something else. And wait. His displacement vector was 100, 0, not 120, 0. Okay, so now so this is basically his situation, right? Now again, keep in mind that for the purposes of what I'm drawing here, I'm getting rid of the hill, because the hill isn't really relevant. It doesn't have anything to do with what we're talking about. I've just sort of brought the hill back down to normal. Now watch what happens if I do dot product F and D, right? I get our answer, 11276 newtons. So the first thing that the dot product is good for is we can say the work done is equal to the force vector. Okay, oops. F vec dot, okay, the D vector. Okay, so this is, and the work done is not a vector. It's just a quantity. It's an amount of energy. It does not have a vector sign on it. Okay, so work is equal to force dot distance. This new product is called the dot product. Okay, and what it does is it turns the two vectors into a scalar. It's good for length. It's good for when you're doing these questions about work. It's good for angles, and it's good for projections. Okay, now where does the dot product come from? It comes from, okay, so let's type it out again. So F dot D, how did we actually solve the work? F dot D was the magnitude of F, okay, multiplied by the magnitude of D times the cosine of the angle in between the two vectors, right? Because, if you go back up to our solution, the force in the direction of motion was the whole force, 120, times the cos of the angle in between the two vectors. So like F cos theta is how we got the 11276, and then D is where we got the 100. Okay, so here's the first really important idea just to understand. The dot product of two vectors is the magnitude of one times the magnitude of the other times the cosine of the angle in between the vectors. Remember, the angle in between the vectors is always given by A, O, and then O plus F. The angle between the vectors is always given as though the two vectors started from the same place, right? So when I say theta, I specifically mean that angle, okay? So it says two vectors A and B have an angle between them of theta. Again, this is what the picture should look like. The dot product is magnitude A times magnitude B times cos theta. Remember, theta is always a number less than 180, because if theta was bigger than 180, you would have a shorter angle on the other side. So you always take the shorter angle between the two vectors. Okay? So again, the dot product is the two vectors, multiply their magnitudes, and then multiply by the cosine of the angle in between them. The dot product is known as the scalar product, scalar with an A. Scalar product, since when you multiply two vectors together, you still get a scalar as an answer. Furthermore, you can actually get a negative answer from dotting two vectors together. That's possible. Okay? Let's think about how that would happen. How could you get a negative? Well, the magnitude of F is always positive. The magnitude of D is always positive. Cos theta, though, can be negative, right, if theta is bigger than 90 degrees. So that's where this little chart is coming from. If theta is in between 0 and 90, cos theta is positive, so the dot product will be positive. If theta is 90, then cos theta is 0, so the dot product is 0. Okay? Probably the most important thing for the next 3 weeks in the course is right here. If two vectors dot to make 0, they are perpendicular. And if they're perpendicular, they dot to make 0 because of this reason. Okay? Because cos theta, the cos of the angle between them, would be 0 degrees. Let's quickly demonstrate that with two vectors that we know are perpendicular. So imagine I draw vector I, which we know is 1, 0, and then vector j, which is 0, 1. Okay, if I dot these two together, so dot ij, I get 0 because they are perpendicular. Now suppose I make another vector that's like, let's not call it k so it's not confusing. Let's say it's u is negative 1, negative 1. Okay, so I'm going to put it over there. Now, the angle that this makes with either of the other two vectors is bigger than 90, right? So if I dot iu, I get a negative. If I dot uj, I get a negative, because the angle between them is bigger than 90 degrees. Okay? Now, when the angle is between 90 and 180, cos is negative, therefore the dot product is negative. Okay, this little chart here is really important. I will definitely ask you about this, so come back to it. It's easy to forget, right? But I want you to come back to this and think about it. Calculate the dot product of two geometric vectors. two vectors A and B are placed tail to tail and have magnitudes of 3 and 5. There's an angle of 120 between the vectors. Find A dot B and B dot A. Okay, so let's draw it, get the answer, and then we'll come back to this. So let's make a point O. Then let's make a circle O that's magnitude 5. We'll pick a random spot on that circle, and we'll go vector OA. Now vector OA has a magnitude of, magnitude OA, this is supposed to be the magnitude of 3, so let's call this, let's call this vector B, and we'll rename this to B. Okay, so there's vector B. It has a magnitude of 5. Now I need another vector with magnitude 3, so let's go circle O3. Let's pick a point here. Let's actually take this point. Let's rotate that point 120 degrees because it needs to be over there. And then let's go vector OA prime, and we'll call this vector A. Okay, now let's get rid of the circles. We don't need them anymore. We need that. Don't need that. Don't need that. Okay, so here are two vectors I drew that have nothing to do with one another, except that one is magnitude 3, one is magnitude 5, and they have an angle between them, sorry, I actually do need that point, of 120 degrees, as you can see here. Okay? Now, what happens when I dot these things together? So let's dot AB. It comes up with this number, negative 7.55. We'll just 7.5471. Okay? Now what if I do, just for the sake of argument, let's do dot BA and dot AB. You see they're the same. So the order that you dot things in doesn't matter. You get the same answer either way. So let's see how you would do this. So, okay, AVEC. I don't know if there's a quick way to make a dot. Should probably try and figure that out, but BVEC equals, okay, magnitude A, magnitude B times cos of the angle in between them. Okay, again, I should have little vector signs on here just for the notes, I guess. Okay, AB cos theta. The other one would be the same thing. So it's just 3 times 5 times cos of 120 degrees, and that's equal to 15. Cos of 120 would be, let's see, the reference angle is 60, and the cos of 60 is 1/2. So how did this, why is this, oh, maybe my point isn't in the right place exactly. Let me pause and think about this. Okay, again, it was just the curse of drawing something that I thought was accurate that actually wasn't quite accurate. I just, this point A wasn't in the perfect spot. When it is in the perfect spot, you see you get negative 7.5, not the number I had before, as my A was in the wrong place. So anyway, so you go here times negative 1/2, and therefore you get negative 7.5, and that is the actual dot product of those two vectors. Again, if you dot B and A, you get the same answer. So let's just record this, that A dot B is equal to B dot A. It doesn't matter what order you do them in. Okay, it says that the vectors are tail to tail, but not every question is going to bother with that because the angle between two vectors means they are tail to tail. So you had that's always going to be what theta means. Okay, what do we know about the dot product? It gives you a scalar, which is kind of interesting. It gives you a number. It doesn't give you a vector. You multiply two vectors together, but you get a number back. It is commutative in the sense that the order in which you dot doesn't matter. It is distributive. If you dot A with B plus C, it would be the same as A dot B plus A dot C. However, you should also recognize that this, maybe I'll post it, maybe I'll leave this as an answer. Post this on the website maybe, is undefined. And I'm wondering maybe if you can explain to me why that's undefined. Okay? the associative property with a scalar. If you were to scale A and then dot with B, it would be the same as scaling B and dotting with A. It would also actually be the same with simply scaling the dot product itself, because K is a scalar, and you can multiply a scalar times a scalar. That works, right? Two non-zero vectors are perpendicular if A dot B is 0. Okay, again, could not stress more how important that line is. You just have to trust me on this, that knowing when things are perpendicular in 3D is how you get around. It's like adding up numbers in 2D. It's really, really important. For now, all you need to remember is just what this says. A dot B is 0 means the vectors are perpendicular. If A dots with itself, it's the equivalent of simply squaring the magnitude, because recall cos of 0 is 1. So you'd have magnitude A times cos 0, because there'd be 0 angle between two vectors that are the same, that are equivalent. And so you just have A times 1, so you have A squared. So that also is an important property, but again, what I highlighted is what's really, really meaningful. Okay, finding an angle between two non-zero vectors. Again, very important task. How do you find an angle between two vectors? Given that the dot product is equal to AB cos theta, right, then cos theta must be equal to, so let's just rearrange the formula. We get our second most useful formula of the day. Okay, cos theta is always going to be equal to vector A dot vector B, okay, divided by magnitude A magnitude B. I'll bring the A on top because I actually really want to make sure this is clear. Okay, so this also is a very, very important formula, because this is how you get the angle of anything, again, in 2D or 3D. To get the angle between two vectors, compare the dot product with the magnitude, do the inverse cos. You don't have to worry about which quadrant it's in, because either cos will always tell you it's in quadrant 1 or quadrant 2, and that's what the angle between two vectors always is. It's always either less than 90 or less than 180, right? Like it's in between, sorry, I should say it's either between 0 and 90 or between 90 and 180. And cos gives you those answers exactly. So there's nothing to worry about doing inverse cos here. It just gives you theta directly. Now, this, of course, you should be wondering, well, okay, so what? If the only way for me to get the dot product is to know the theta in the first place. So we need to come up with a way to get the dot product without knowing the theta. And here's where the really interesting stuff begins. You can find the dot product for algebraic vectors by multiplying the two x components together, and then multiplying the two y components together, and then adding them. Allow me to demonstrate. Let's make up two vectors. Okay, let's say we have vector, here's, let's put it like so, and like so. Okay, now when I dot UV, it comes up with the answer 14. Where does 14 come from? X times x gives me 16. 1 times negative 2 gives me negative 2. And I go 16 plus negative 2 gives me 14. Okay? And so I could calculate the angle between these vectors because I know the dot product is 14. I know the magnitude is square root 17 times square root, what would that be? 16 plus square root 20. Okay? Square root 17 times square root 20. And I do the inverse cos of b, and that tells me the angle between these two vectors is 40.6. And when I measure it, right, 40.6, right down to the, as far as you want to go. So this is major. To dot two vectors together, if they are in Cartesian form, which is component form, you simply multiply the x coordinates, multiply the y coordinates, and then add them all up. In 3D, it's the same thing. X times x plus y times y plus z times z. So that's a1 b1 plus a2 b2 plus a3 b3. Again, this will give you a scalar because it's just a bunch of scalars multiplied and added together. Okay. I times I dot I is just equal to 1. I don't know why. I don't really know what this is. I guess what they want us to say here is I squared, and then that's just equal to 1. I dot j would be 1 times 0, which would be 0, because I and j are perpendicular vectors. J dot j and k dot k are also 1. And j dot I dot k dot I, j dot k, and k dot j are all 0 because they're all perpendicular to each other, right? Again, just to quickly remind us about that for a sec so we're not too lost on that topic, let's just look at the 3D graphics for a minute. Let's draw vector I, which is 1, 0, 0. Then we're going to draw vector j, which is 0, 1, 0. And then vector k, which is 0, 0, 1. And you can see that those three vectors are perpendicular to both of the other two. Right? So if I dot, for example, I and j, gives me 0. If I dot I and k, dot I and k, it gives me 0. And if I dot j and k, it gives me 0. So again, dotting any of those with each other, because they are all perpendicular to each other, is always going to give you 0. Okay? And you can see there, that's like they form the corners of the three things form the edges and the corner of a box. Okay, this is the proof of the where the dot product comes from, like why you're allowed to do this. This is actually a really interesting proof to look at. I'll just talk about it. I don't think I'll go through it. In this triangle, right, you have vector b and vector a with the angle between them, and then you have vector c. Now, of course, vector c would be vector a minus b, because I start up here, I go in the direction of negative b, and then a positive a gets me down to here. So that tells me vector c, right, is a subtract b. So this is also a vector a1 minus b1, a2 minus b2. So what they do then is they do the cosine law, and they replace, this thing on the left with the dot product, because ab cos theta is the dot product. And what you have up here is you have a squared plus b squared minus c squared. They replace all of this with their components, they clear it all up, and you come up with this. So the dot product's on the left, and a1 b1 plus a2 b2 is on the right. I think this is a really good exercise to try to do. I probably won't ask you to do this, but I will not ask you to do this, but I do think it's a very good exercise for you to try. It will sort of test your skills as like, am I getting this or not? Give this a shot. If you're not getting it, say this, I got this far, what do I do next? Okay, so let's try some simple vectors here. So how do I get the dot product of 1, 2, negative 4? So let's just wipe out what I have here. So my first vector is a. It's 1, 2, negative 4. Again, where is that? It's a positive in the x, so it's positive in the red, it's positive in the green, but it's negative in the blue, right? So it kind of points under the page, so to speak. Okay? So there you go. Some vector down there in the bottom. Now I have another vector. B is 3, 4, negative 5. Okay? So that again is sort of in a similar region. Points down, sort of more, if it goes down further, but it's also sort of wider out. Now if I dot these things together, I get 31. How did I get 31? So to a dot b, okay, a dot b would be 1 times 3 plus 2 times 4 plus negative 4 times negative 5. Okay, what happens there? A dot B is equal to 3 plus 8 plus 20, which is 31. And that's why when they dotted together, they got 31. Now, what this should get you thinking is, now you have a way to find the angle between two things in 3D, which, how would you possibly do that before knowing this? You can get the angle between these two vectors, right? Because I know that the dot product divided by the magnitude, so I'm going to do 31 divided by length A times length B. So put those in brackets on the bottom. So this would be the dot product over the two magnitudes. Okay, is that, and then if I do the inverse cos of that, I get 16.93, which is the angle between A and B. Okay, so again, it can be difficult to see these things, but right, that little angle down there actually might help if I get rid of the axis. Actually, I'd get rid of the plane too, for that matter. Okay, so those are my two vectors, and the angle between them is that 16.93 degrees. Okay, find a value k so that 1, 1, 1 and k squared negative 2k 1 are perpendicular. Okay, 1, 1, 1. Now the symbol for perpendicular, it's probably helpful to know. I think it's one of these things, but sorry, I'll pause it.